All right, welcome back. So again, we're dealing with how to handle the transformation rules and how to get from the forward to the reverse or inverse transformations. So that's what we want to do here. We're looking at for solve equations for or 12.18 for x, y, z, t in terms of their transformed coordinates, and check that you recover equations 12.19. All right, so this is not too bad, I don't think, but it definitely is a need for know, and we get quick rules from that. We just got to be careful, of course, with the plus and minus signs, of course. So we know that if we're moving along the x direction, we have a Lorentz contraction, and we also have a time dilation going on in the system. So if we have x, y, z, and t, then we have the forward transformations here on the left, and then we have the inverse on the right. Okay, the easy part is y bar and z bar stay unmet or untouched rather, and we're just going to have to look at some characteristics between the x and x bar and t bar. Let's dive in. So, starting with the set of equations on the left, we solve for equation 4 for t and plug it into 1 and solve for x. So t bar gives us this. Let's solve it for t. So we divide over gamma, and that gives us t minus v over c x. So solve everything again by adding that over. That gives us a final thing for t, final expression or equation technically. So if we plug it into the t here that we see in the that we see from equation 1 in the forward, then we see that we distribute the gammas, and then we can plug in the t, and now we can write everything in terms of t bar and x on the right hand side. So eventually we'll have to solve for x out of this. So here, go ahead and distribute the gamma into the parentheses, or gamma v into both. And we see here that we still recover the gamma x, but we see we had a gamma cancel with gamma on the vt term. Easy enough. And then we see we get a minus sign that we need to take care of. So let's be careful there. That should be minus as well. But we need to make sure that we know that the v goes to v squared, and we're left with c squared there, so we're fine, everything there. Now we see that we have a gamma and a gamma with this v all multiplied by x, so we can actually factor out a gamma x from those two, and we're left with a 1 minus v squared over c squared. So just note that this was a minus as well, and it's recovered right there. This minus goes right here to the vt bar. So that being said, this parentheses term is actually the squared Lorentz factor, but it needs to be the reciprocal. So that's where we put the 1 over gamma squared here. And then we see that the factor of gamma cancels gamma. Easy enough. So what we see in this is that x bar is equal to x times 1 over gamma minus vt bar. Clearly add the vt over, and now we're left with x over gamma on one side, so multiply the gamma over. And we're left with x equal gamma x bar plus vt. Similarly, we could do this back sub method. Solve 1 for x and plug it into 4 and solve it away for t. And when we do this, we get exactly what we expect. T is equal to gamma t bar plus v over c squared x bar. Deal with system of equations, not too bad. We've seen it before. Algebra comes through. That being said, we actually have a really easy transformation for, or at least rules for them, where we're just switching the bars and the minus signs, things of that nature. Look at these little symmetries because they'll pop up again later. And yeah, we'll catch you at the next one.